we talked about this already, but I just want to emphasize it one more time that these things are pretty much interchangeable. If we have a factor of x plus c, that's the same thing as saying x equals negative c is a 0, and it also means that negative c comma 0 would be a point. Okay, so all of that language is interchangeable. And the number of real zeros, I don't know what that's supposed to say, but I'm thinking would be n at most. Okay, if we've got a third degree polynomial, at most we're going to get 3 real zeros. Okay, if we've got a fourth degree polynomial, then at most we're going to get real zeros. Okay, so that's what we'll be looking for. Okay, so here we have the rational zeros theorem. If we have f of x, which is a polynomial function with integer coefficients, and p over q is a rational number in lowest terms, that is a 0 of f of x. So we've come up with something. We know these things are rational zeros. They're real numbers. Then if this is the case, it says p is a factor of the constant term, and q is a factor of the leading coefficient. So if we're going to get these real zeros, then they have to be written as a factor of this thing and a factor of this thing. Okay, the a sub 0 and a sub n. So we can come up with a list of possibilities. All right, that's what we're going to start with. So it says find the set of possible rational zeros of the given function. And so this would be my p. It doesn't have many factors, thankfully. This is my q. Okay, I'm going to write, I'll just say p equals 1. Its factors are just what? Plus minus 1. Okay, because negative 1 times negative 1 is 1. And then q, we've got factors of what? Plus, and also plus minus 1. Right? Plus minus 1, plus minus 2. Okay, so then the list of possible rational zeros takes every possible p-value, and puts it over every q-value. So I would say plus minus 1 over plus minus 1, which is just 1. We didn't have to write all that, but to make the point, plus minus 1 over plus minus 2. Okay, so my list of rational zeros is plus minus 1 and plus minus 1/2. Okay, if I had a p-value, then I would take that and put it over every q. Okay, every p-value, I'll put it over every q to come up with my list of possible rational zeros. Okay, so if there's a rational zero, rational means I can write it as a fraction. I think we know what real numbers are. They're not the imaginary numbers. So if we're going to have a rational zero, it has to be one of these numbers. Okay, in B, I'm going to again look at my constant. So what are the factors of 35? Okay, 5 and 7 plus minus 5 plus minus 7. Don't forget about 1. It's a factor of everything, and that goes with what? Okay, 35. Very good. Okay, and then for 6, it's going to be what? Okay. All right, so that's my P and Q values. So my list of possible rational zeros is going to be plus minus 1, plus minus 5, plus minus 7, plus minus 35, plus minus 1/2, plus minus 5 halves, plus minus 7 halves, plus minus 35 halves. I took all of the p-values and put them over 2. Now I've got to take all of them and put them over 3. Plus minus 1/3, plus minus 5/3, plus minus 7/3, plus minus 35/3. And then finally, take all of them and put them over 6. And so we get plus minus 1/6, plus minus 5/6, plus minus 7/6, and plus minus 35/6. Okay? That's the list of possibilities. That's a lot of values. We'll talk about some ways to reduce that list using some other theorems that we're going to talk about. But if there's a rational real zero, then it has to be amongst this list. Okay, questions about coming up with that list? Okay, very good. All right, so we want to actually go through the process and find all of the rational zeros of the given polynomial function. We're going to start by listing all possible rational zeros, and then we're going to use synthetic division to determine which ones are zeros and which ones are not. We're going to reduce the polynomial and continue the process. Okay, so starting with a pretty simple example, we've got plus minus 1, right? And over here, plus minus 1, plus minus 2, plus minus 3, plus minus 6. And this actually turned out to be our list, right? Did I make something up? Is it okay? Y'all were so quiet. Okay. So our list turns out to be plus minus 1, plus minus 2, plus minus 3, plus minus 6. And we just have to pick a value and go to it using synthetic division to try to determine if it is a zero. So I'll just start with positive 1 because I don't know what the answer is. So we've got 1 minus 4, 1, and 6. Bring the 1 down. 1 times 1 is 1. We get negative 3, and 1 is negative 3. Add again, we get negative 2. I got 4. So that's not a zero. Okay, so I have to use something else. So I'm going to try 2. Okay, we get 1 times 2 is 2, which gives me negative 2. Negative 2 and 2 is negative 4. Negative 3 and 2 is negative 6. I get 0. Okay, so that worked out. Okay, we're going to factor this thing. So how do I do that? Well, now I can say f of x equals x minus 2. And that comes from here because 2 was a 0. And remember what we said about those 3 different ways we can state that? If 2 is a 0, then what has to be a factor? X minus 2, right? Does that make sense? Okay. 2 is a 0, so x minus 2 is a factor. We divide it by... basically, we're dividing by x to the first. So since we started with x cubed, then this starts with what? X squared. So this is x squared minus 2x minus 3. Okay? And from there, if we needed to, we would generate a new list of possibilities and go to it again. However, in this case, I think we can factor. And so this factors as x minus 3 times x plus 1. Okay, make sure we answered all of, or answered the question. They want us to actually find the rational zeros. So we would say x equals -1, 2, or 3. That's our answer. Questions about that? Okay, very good. All right. So we're going to do the same thing with this other one. It's a little bit larger, but that's okay. We can handle it. Why don't you start the problem by coming up with the list of possibilities, and then we'll go from there. All right, so that's our list of possibilities. Okay, how many people got that? Okay, good. And as where to get 1/2 from? Once we put all of these over 1, then we had to come back and put them all over 2 as well. So when we said 1 over 2, that gave me 1/2. And then we would say 2 over 2, but I didn't write that one because that's the same thing as 1. We already had that in our list. And 4 over 2 was the same thing as 2. That was also in our list. Okay, but we take all the p's, we have to put them over each of the q's. Okay? So now that we've got our list, okay, we're going to go ahead and start trying some of them. You can try some as well. I'm going to start with 1 again and hope for the best. 2, 3, 8, 3, -4. Bring down the 2. 2 times 1 is 2. We got 5. 5 times 1 is 5. Gives me 13. 13 times 1 is 13. That gives me 16. 16 times 1 is too big. Okay, so that did not work. Okay, however, this might be a good time to point out something very interesting here. Let me just look quickly. Okay, this is a special situation that we're going to talk about a little bit later. Okay, in this case, our value here is greater than 0, and it turns out that this bottom row is all positive. Okay, this is an indication to me that this is an upper bound, right? Meaning that there's no need to go higher than 1. All right, we'll introduce that a little bit later formally, but those are the kinds of clues that are going to help us break this list down so we don't have to try everything. If you tried a positive value here and you get all positives in your bottom row, that means that 1 is an upper bound. Any real zeros that we're going to have, they have to be less than 1. So there's no need for me to try +2, +4. Okay? All right, so we're going to go in the other direction. All right, we get -1. 2, 3, 8, 3, -4. 2, -2 is 1. 1 and -1 is -1, right? Which gives me 7. 7 and -1 is -7. This gives me -4. -4 and -1 is 4. I get 0. Okay, so we found one, and so now I can write this as x plus 1, very good, times, okay, plus x squared plus 7x minus 4. Okay, so that's how far we've been able to break it down. From there, you know, we either come up with another list, or if we could factor it, we would do that. Okay, so I'm going to come up with another list. we'll see some of the same values, but I'm using this piece now to come up with my new list. So when I look at P, in this case, I get plus minus 1, plus minus 2, plus minus 4 again. These are the same values we had before. Is that right? Okay. It doesn't have to be that way. But in this case it is. So we'll still use those. However, what we learned about the upper bound, that still applies. Okay. So no need for us to go continue in that direction. Okay. So what value? We'll try negative 2. So I'm going to do negative 2. And this time we're looking at 2, 1, 7, negative 4. Going to bring the 2 down. 2 times negative 2 is what? Negative 4. Add, we get negative 3. Negative 3 and negative 2 is 6. So we get 13. 13 and negative 2 is negative 26. We get negative 30. Okay, that does not work. However, let me check to see if this is our other rule. Okay. This time we used a k value that was less than 0. And what kind of pattern do you see happening here in our last row? Positive, negative. It's alternating. Okay. So that shows us that this is going to be a lower bound. Okay, so there's no need for us to go less than negative 2. All right, it's nothing above 1. There's nothing below 2. So at this point, either we've got some imaginary numbers, or we could try negative 1 again. Okay, because we can have repeated zeros, right? We talked last week about multiplicity. Remember that? Okay, so it's worth it to try it again. So let's just give him another shot and see if that works. All right, so we got negative 1. I'm going to put that into 2, 1, 7, negative 4. Bring the 2 down. 2 times negative 1 is negative 2. We get negative 1. Negative 1 and negative 1 is 1. That doesn't work. We get 8. 8 and negative 1 gives us negative 8. I got negative 12. Okay, so it looks like then possibly we don't have any more real zeros for this polynomial. Okay, what's that? Oh, I forgot that one. Thanks. I forgot about the fractions. Okay, 1/2. Okay, so 2 times 1/2 is 1. Okay, we get 2. 2 times 1/2 is 1 again. We get 8, and 8 times 1/2 is 4. We get 0. Very good. All right, thank you. All right, so now we can write this as f of x equals, we already had x plus 1. Okay, and now we can write this as x minus 1/2, and we're left with what? 2x squared plus 2x plus 8. Okay, 2x squared plus 2x plus 8. And hopefully at that point we can factor. Okay. I know you never thought you'd be very glad to factor, but we'll be glad to factor when we get there. Okay, we can certainly factor out a 2. We're left with x squared plus x plus 4. Okay, and just looking at that, do you think it factors? I don't think so. Okay, so we're left there. If we had to, going back to the instructions in this problem, they wanted us just to find all the rational zeros. And so we could stop here. We would say our zeros are x equals negative 2 and x equals 1/2. Would I change what? The first one was x plus 1. No, there should be a 1. Okay, so we get x equals -1. Yeah, I was looking here, but it was right here. That's right. Okay, very good. Questions about that? This is a mainstay of chapter 3, being able to find these zeros. Okay, this is not going away, so you can't say I'll just miss that one on the test. All right. Okay, very good. All right, let's see what's next. Okay, so yes, here's what I was telling you about. Well, here's actually another rule that's going to be useful to us. This is Descartes' rule of signs. This tells us about the possible number of positive and negative zeros. Okay, a variation of signs occurs when the signs of two consecutive terms differ, when the terms of the polynomial are written in descending order. Okay, so it says let f of x be a polynomial function with real coefficients and with terms written in descending order. The number of positive zeros of f of x is equal to the number of variations of sign of f of x, or is less than that number by an even integer. So we look at the polynomial and we count the number of times the sign changes. All right, whatever that comes up to be, then it's either going to be that number or a multiple of 2 less than that. When it says either that or different by an even integer, let's say we found 11 sign changes, then we're either going to have 11 positive zeros, 9 positive zeros, 7, 5, 3, or 1. Okay, it has to differ by an even integer. All right. Okay, and how could we use that information? Let's say we're going along and we found, in the example that I just mentioned, what did I say? Okay, let's say we found 2 positive zeros. All right, then based on that, I know I need to try for one more positive because it has to be an odd number in that example. Does that make sense? Okay, all right. That's right. Less than that. That's right. Okay. All right. So that's for positive zeros. We just look at f of x. The number of negative zeros of f is equal to the number of sign changes in f of negative x, or is less than that number by an even integer. Okay. When using Descartes' rule, a zero of multiplicity m should be counted as m zeros. So when we talk about finding one positive zero, if we find the same one multiple times, then we count all the times that we found it. Okay? Does that make sense? Okay, good. I'm getting some nods. The rest of y'all are somewhere else. I need y'all to come back here. Okay. Determine the possible number of positive and negative zeros of the given function by using Descartes' rule of signs. So, for positive zeros, I look at f of x, and when I look at this, we start out positive, positive, then I've got one change, right? And that's it. So there's going to be one positive zero. How is there? How is there only one positive? Well, we have to look at the sign changes. So when we were positive here, and when we went here, we were still positive. That's not a sign change. Right? They do need to be in order of descending power. So we had a cube, then squared, then first degree, then constant. So we only have one sign change from here to here. No, it's just the sign changes as we go from one term to the next in order of descending power. Okay? All right. Okay, for negative zeros, we're going to look at what? f of negative x. So first of all, that means you got to be able to figure out what f of negative x is. Okay? And so f of negative x, we got to plug that in. Wherever we had x, we're putting in negative x. So we get 3 times negative x cubed plus negative x squared minus 9 times negative x minus 3. So we get minus 3x cubed plus x squared plus 9x minus 3. Okay, that's f of negative x. And so we got one sign change, two sign changes. So we could have 2 or 0 negative zeros. All right. Negative x times negative x is x squared. Did I miss? Yeah, that's right. Okay. Other questions? All right, very good. So given this information, if we had a list of possibilities, where do you think you would start? Would you start with positive numbers or negative numbers? Positive. You know that there's one positive 0, right? You know that. So it'd be good, nice to start, try to figure out that one, and then, come back here. There might not be any negative zeros. We're not certain. It could be 2 or 0. So I would start with the certainty here. Okay, very good. All right, why don't you try that on your own in example B. Nope. Nope. It has to be whatever number we have in this list, the numbers we have in this list, that's what it can be. Okay. How do we know if it's positive or negative? Based on the rule says, first of all, we look at f of x. That lets us know about positive zeros. All right. Now, to figure out the negative zeros, we have to look at f of negative x. Okay, so that's the second part of it. So I'm going to first find f of negative x, which is going to be 3x to the 4th minus 8x cubed, okay, minus 5x squared plus x plus 2. And then I count the sign changes. So that's 1, 2. So it's going to be 2 or 0 negative zeros. Okay, so that's how. We look at sign changes in f of x for positive zeros. We look at them in f of negative x for negative zeros. It could have no real zeros. And so eventually we will start looking for the complex zeros. Okay, we're going to find all of them. That they could have no real zeros? Yes. And what does that look like graphically? If we say that it has no real zeros, that means it also has no intercepts. So think about a quadratic equation. And I think we did this the other day, but a quadratic equation, first of all, it's a second degree polynomial, so at most it can have 2 real zeros, right? We saw a situation where it might have 1 0, okay? Or situations where it has no zeros. It never touches it. All right, no real zeros. So then we would have to find complex numbers. That's when you were using the quadratic formula and coming up with that imaginary solution. Remember that? Okay, that's a situation like one of these. Okay, very good. So lots of little clues to try to help us. And then here is what I mentioned earlier about the upper and lower bounds. I think. It says if a polynomial function f of x has no zeros greater than a number k, then we call k an upper bound on the zeros of f of x. If f of x has no zeros less than a number k, k is called a lower bound on the zeros of f of x. These bounds have the following rules. Okay, first, here's the short of it. If k is less than 0 and each number in the last row is 0 or positive, then k is an upper bound on the zeros of f of x. And we saw that in the earlier example. Okay? If k is less than 0 and the numbers in the last row alternate in sign, then k is a lower bound on the zeros of f of x. All right, we also saw that in the example. We'll just look back here real quickly at it. Right, where was it? Was it this example? Yeah, right here. Okay, right here we had a situation where we had all positive values. The k value that we put in was positive, so this is an indication of upper bound. Okay, this would be an upper bound. All right, and then down here we saw where it was alternating. Okay, and so in that case we also, and we had to have a negative value here. So with the alternating, we could say that that was a lower bound.
Would it also work on where we did -1 and it was 2, -1, 8, -12?
Yes. Yes, very good. Okay, again, it showed that this was still a lower bound. And then we went back and found a number that was between -2 and +1. The other zero that we found was between the two of them. Okay, not outside of that range. Okay, very good. All negative zeros? Sure, that's possible. Okay, you can have all negative or all positive. It just depends on where it intercepts that x-axis. Okay.
So if it's all negative, it would be the same as
Yes, we would find that using Descartes' rule of sign. Okay? Alrighty, did we do that? Determine upper and lower bounds of the given function. Okay, they want us to try to find some upper and lower bounds. So let's see if we can do that. First of all, we're going to come up with a list of possibilities. So we got plus minus for p's. We've got plus minus 21 and plus minus 1. And then what, 3 and 7? For q, we've just got plus minus 1 and 2. So our list of possibilities is plus minus 1, plus minus 3, plus minus 7, plus minus 21, and then 1/2, 3/2, 7/2, and 21/2. Okay? All right, so that's our list of possibilities. All right. Right here. Here. This is 7/2 and then plus minus 21/2. Oh yeah, plus minus 21. Yes, right here. Okay, plus minus 21. Okay, so we start then. That's why I'm kind of starting from the middle, you know, right there at 1. And then going, so that once we hit that upper bound, we don't have to go up any farther. Okay. So we just got to try them out. We're going to try 1. We've got 2, -3, -14, and 21. 2 times 1 is 2. We get -1. That gives us -1, which is -15. -15 and 1 is what? And that gives us 6. That tells us nothing. Okay? we could have used our information about positive zeros and negative zeros. How many positive zeros do we expect to have? 2 or 0, okay? 2 or 0 positive zeros. All right, so we'll keep going in this direction. The next one then that I'm going to try is 3. Okay, 3 times 3 is 9, which gives me -5, -5 and 3, -15. That does not work either. That's interesting. Okay, and still doesn't tell us anything. Okay, what else do we have? Let's go ahead and try 7. Two and 7 is 14. We get 11. 11 and 7 is 77. I'm pretty certain that's not going to work. And this is certainly going to be a positive number. And then we're going to get another positive number, which tells us what? Upper bound. We don't need to try 21. Okay? So, and we've got some positive zeros. So where else could we go? We did 1, 3, 7. We're not going to try him, so we need to look at some of these fractions. Let's try. Somebody's got one? 1/2? Okay. 1/2 seems to be the winner today. Okay, bring down 2. 2 times 1/2 is 1. We get -2. -2 and 1/2 is -1. I got -15. Did I miss something? Okay. All right. So that one didn't work. We get -7/2. We don't even want to look at that. It doesn't work. Okay. 3/2. Okay. 2, -3, -14, 21. Bring down the 2. 2 times 3/2 gives us 3. That's a nice 0. 0 and 3/2 is 0. We get -14. -14 and 3/2 is -21. And so we get 0. And then we even stop and ask ourselves, determine the upper and lower bounds. And we got so excited that we had to answer. 7 was an upper bound. We could have stopped back there. I forgot what the question was. All right. So we did find that 7 is an upper bound. And we also found one of the zeros. Okay. All right. To find a lower bound, it has to work on what kind of number? A negative number. Okay. So when we start trying the different negative ones, we're looking for that alternating pattern. Does anybody have one already? Okay. If not, then we'll just try some. 2 times -1 is -2. We get -5. -5 and -1 is 5. We get -9. -9 and -1 is 9. Not alternating. Okay. Try -2. Which -2? Right here? Okay. Right here? I don't know. I made that up. Let's try -3. Okay, is that better? All right. So bring down the 2. 2 times -3 is -6. So we get -9. -9 and -3 is 27. Is that right? And so we got 13. 13 and -3 is -39. We get another negative number, which means what? Lower bound. Okay? We can say that -3 is a lower bound. Okay, questions about that? Yes. You could have, I mean, once you find that something is an upper bound, then anything above that would be an upper bound as well. But this isn't a tool that we just kind of use isolated. The whole point of this is to help us find those zeros. So we're kind of looking at it isolated right now just to interpret it. But if we were really going for the zeros, then we would use it just the way we did here. Once I found that 7 was an upper bound, there was no need for me to try 21. Because 21 is greater than 7. And what our ultimate goal is going to be to find these zeros. Not just to figure out what's an upper bound and what's not. Well, it is in this case, but like I said, in a practical sense, and the way that we're going to actually use this, once we found an upper bound, there's no need to keep going. And if 7 is an upper bound, so is 21. If we put 21 in there, then it would have all positives just like the 7 does. Okay.
So for it to be upper bound means that's the highest number.
Well, it's not going to be higher than that. Okay. It has to be between the upper bound and lower bound. Okay. So again, once we got to 7 and saw that it was an upper bound, there was no need to go on to 21. Okay. Once we find here that -3 is a lower bound, we don't need to look at -7 and -21. Okay. Questions about that? Very good. I think we beat that to a pulp. Okay. All right, find the real zeros of a polynomial function. I think we're going to go for it. Okay, here's just a little strategy. Find the maximum number of real zeros by using the degree of the polynomial function. Find the possible number of positive and negative zeros by using Descartes' rule of sign. Write the set of possible rational zeros. Test the integer from the list above to find zeros and upper and lower bounds of the real integers. Okay, test the positive fractions that remain in set 3. In the set in step 3 after considering any bound that has been found. Is that the last step? More steps. We modify, we repeat, we rewrite the equation in a simpler form until we find all of them. Okay? So let's see what we can do. Actually, make this a little smaller. Okay, so we're going to find the maximum number of real zeros. And of course, that's just going to be what? 5. Okay, the degree of the polynomial, that's what that little short sentence earlier told us. The degree of the polynomial lets us know the maximum number of zeros that we're going to have. Okay, if it's quadratic, which is a second degree polynomial, at most we're going to have 2 real zeros. This is a 5th degree polynomial, so at most we're going to have 5 real zeros. Okay, all right. Then we're going to find the possible number of positive and negatives. So for positives, we look at what? Okay, we want to see the sign changes in f of x. And so we have how many? Okay, 2. So it's 2 or 0 positive zeros. Okay, then for the negatives, we look at f of negative x, which in this case is negative x to the 5th plus x to the 4th plus 6x cubed minus 6x squared minus 8x plus 8. All right, so how many sign changes do we have? 3. Okay, so we could have 3 or 1 negative zeros. Because remember we said we decrease it by an even number.
Oh, okay.
So, and you remember you said earlier if it's odd it would be odd numbers. If it's even it'll be the even numbers. Okay. Okay, very good. All right, now we're ready to write our set of possibilities. And someone was nice to us. They let Q be 1. So our list of possibilities is just going to be the factors of P, which would be what? Okay, very good. All right, plus minus 1, 2, 4, and 8. Okay, because we're putting all of those over plus minus 1. All right, and so we're going to test the integer from the list above to find zeros and upper and lower bounds of the real integers. Okay, so we actually start now. Where do you think we should start? Positive zeros or negative zeros? Okay. Positive, did you find one already? Okay. All right, you want to start with negative? Okay, fine. Negative 1, I would start with negative 2 if I didn't know what the answer is, which I don't. All right, we got minus 6, 8, and 8. Okay, bring the 1 down. 1 and negative 1 is negative 1. We get 0. 0 and negative 1 is 0. We get negative 6. Negative 6, we get 6, which is 0. 0 and negative 1 is 0. Gives me 8. Yay, we found one. Okay. So first of all, we found that negative 1 is a 0. As far as alternating, let me see what he says here. Okay, for this, when it looks at the number of, or rather the lower bound, he says that zeros can be considered positive or negative, whatever makes the pattern work. But in that case, no matter what, if this is positive, it doesn't work. If it's negative, it doesn't work. So that's not a lower bound. Okay? All right, but we did find one, and so now we can write this as what? Okay, x to the 4th. Well, this would be 4th, this would be 3rd, so this would be squared, okay, plus 8. Okay, that's where we are now. Okay, questions about how we were able to reduce the polynomial? Okay, good. All right, and so now we try another. We did find one negative 0. Yes? No, this would be plus 8 because this last one is going to be our constant. So this is, we started with x to the 5th, so this is x to the 4th, x cubed, x squared, x, and this is our constant. Okay. And that's the remainder. Okay, other questions about that? All right, why don't you see if you could reduce this x to the 4th minus 6x squared plus 8, and then we'll go from there. All right, so if we try negative 2, okay, starting here, we get 1, 0, negative 6, 0, and 8. Okay, so bring down the 1. 1 and negative 2 is negative 2. We get negative 2. Negative 2 and negative 2 is 4. Gives us negative 2. Negative 2 and negative 2 is 4. Okay, and then 4 and negative 2 is negative 8. And so we get 0. And so yes, now I can write f of x as x plus 1 times x plus 2 times, now we're down to cube, so we get x cubed minus 2x squared minus 2x plus 4. Okay? Alright, so from there, we could look at some possibilities. I don't know, I just felt the need to look back at negative 1 and negative 2 and just to check and to make sure they weren't repeated, and they are not repeated. So what else did you try? Two? Okay. Now also the other thing that I was thinking about is we've got two negative zeros, so shouldn't we have a third? Or did I miss that? For negative zeros we said what? 3 or 1. Okay. So that's why I kind of stayed on the negative side once I had the second one. But what did you find that worked? 2? Okay. Let's try 2. Alright, so we get 1 minus 2 minus 2, 4. Bring down the 1. We get 2, 0. That gives us 0, negative 2, and is negative 4. So that works. Okay, so now I can write f of x as okay, then we have x minus 2, and then now we're down to x squared, which is x squared minus 2. Okay, so how are we going to deal with that piece? Yes. Well, let's see. It depends on really what the question is asked. And so just going back up to the top, what did the question ask? I can't see it. Okay. So far we've got 3 real zeros. We can find a real zero here. It's just not rational. So what I would do is say x squared minus 2 equals 0. And that's basically what we've done with all of these. X plus 1 equals 0. That's how that came from x equals negative 1. Right? This one gave us x equals negative 2. This one is where we had x equals 2. So I'm setting this equal to 0 just like we would in college algebra. Well, no, algebra anywhere. And then we get x squared equals 2. X equals what? Plus or minus the square root of 2. There's our other negative one. It's real, it's just not rational. And so our zeros then are minus 1, plus and minus 2, and plus and minus the square root of 2. Once we get it down to a quadratic, we can factor, use a quadratic formula, any of those things to try to solve it. Okay, very good.